For the next several lectures, we're going to talk about theoretical computer science. In many scientific disciplines, people working in the discipline maybe can dismiss theory as something maybe not relevant to what they do daily. For computer science, that's not really true. Theory is an integral part of our discipline, and everyone should have a basic understanding of the type that we're going to talk about in the next couple of lectures. We'll begin with a brief overview of the basic issues. We're going to be talking about very fundamental questions relating to computation, like what can a computer do? Or if we have limited resources, what can we do with a computer? This very general approach that mathematicians and computer scientists have used over the last 5 or 6 decades, actually. First of all, we don't want to talk about specific machines or problems. We want to consider what's called abstract machines that have very minimal capabilities. We'll see some examples of that in this lecture. This is an example of a machine that we'll see at the end. And we'll consider very general classes of problems. So the idea is to come up with the simplest machine that shares the characteristics of the actual machines that we use and the classes of problems that embody the classes of problems that we care about, and try to say general statements. And the surprising outcome of this approach is that we're going to have sweeping and very relevant statements about all computers. It's quite actually an amazing outcome that we'll get to in the next couple of lectures. And it doesn't matter whether it's a supercomputer or a new laptop or your phone or an old PC or an old mainframe or even one of the first computers. All these computers share the same basic properties that we'll be able to articulate really quite precisely. So in general, there's a question of why study theory. Even Yogi Berra had a comment on it. In theory, there's no difference between theory and practice. In practice, there is. And we'll see that right away in this lecture. Certainly, for theoretical computer science, we get a very deep understanding of computation that actually is the foundation of all the modern computers that we use. It really helps us understand the natural world, and there's philosophical implications as well. In practice, there's all kinds of practical tools that have evolved out of the theoretical studies. So when you do web search, you need the theory of pattern matching, which is very related to these basic computational questions. The circuits that we use to build computers, or compilers that we use to translate from one programming language to another. Cryptography is based on theory, data compression, and many, many other fields have evolved from the basic understanding that we get from theoretical studies. So in this lecture, we're going to talk at both levels. We'll talk a little bit about theoretical questions, a little bit about practical questions, and end up with some basic questions about computation. So one thing we're going to talk about, I already mentioned, is the idea of abstract machines. So what an abstract machine is really a mathematical model of computation. Actually, for the lecture, we have kind of a graphical model that mimics what you might imagine a real machine. There's different types of machines. They have different capability. Each machine is defined by very specific rules for taking input and producing output. This lecture, we're going to talk about the simplest kind of abstract machine called a deterministic finite automaton. And that's pictured at left, and we'll look at right, and we'll look at details in a minute. There's another idea called a formal language. A formal language is just a set of strings. Over on the right, we have an example of a set of strings. So that's the set of English language palindromes, say. Does the thing read the same forward and backwards? So that's a specific rule that characterizes this set of strings, reads the same forward and backwards. And you could have imagine many other types of rules. If you can articulate the rules, then you're defining a set of strings. A set of strings is a formal language. So we're going to talk about a particular set of rules called regular expressions today. And those turn out to be very useful in many applications. In this lecture, we're going to address some basic questions related to these abstractions. For example, we might want to know, is a given string in the language defined by a given regular expression or not? That already is an interesting question to approach. And we might say, well, if we had a computer, could we answer this question? In particular, could a simple computer like a DFA answer this question? Already, with these very simple models, we come to interesting questions with useful practical applications. That's what most of this lecture is about. So now let's take a look at regular expressions. Regular expressions are relevant to an important problem known as the pattern matching problem. We want to know, is a given string an element of a given set of strings? Or is it in a language, given language? So here's an example from computational biochemistry. One way to represent an amino acid is with one of the characters, CAVLI, that are listed there. And each one of those is a standard representation of an amino acid. A protein is a string of amino acids, so just a string consisting of those letters. So there's a particular type of protein that is referred to as a C2H2 type zinc finger domain signature. And that's well defined by these specific rules. It's a C followed by 2, 3, or 4 amino acids. It could be any one of them. Followed by another C, followed by exactly 3 amino acids, followed by one of these 9 specific ones, L, I, V, M, F, Y, W, C, or X, followed by 8 more amino acids, followed by H, then followed by 3, 4, or 5 amino acids, followed by H. It's a pretty complicated set of rules, but, well, life is complicated. So we might have the question, I have a given protein, does it follow these rules? Is it in the C2H2 type zinc finger domain? So there's a protein, so let's see if it actually follows these rules, whether it actually follows these rules or not. Is it in the language defined by those rules? Is it in the set of strings defined by those rules? And the answer in this case is yes. It starts with a C, and then there's 3 amino acids, so that's the first bullet point. Then there's another C, and then exactly 3 amino acids. And then the next letter is Y, so that's one of the next to last bullet. That's one of the ones listed. And then there's 8 amino acids. And then the next one is H. And then there's 3, that's okay, the last bullet point, 3, 4, or 5. And then finally an H. So in this case, this string is in the language. And clearly, we want to be able to answer this type of question in a for a broad variety of types of proteins. So that's example 1. Here's another example from commercial computing. Suppose you want to define what an email address is. It's a sequence of letters followed by an @ sign, followed by another non-empty sequence of letters, followed by a dot. Maybe any number of occurrences of that, and then ending up with edu or com or org or gov or some other legal suffix where you would expect to find at the end of an email address. So you can ask then, which of the following are email addresses? So this one's got a sequence of letters, @ signs, some more letters, a dot, some more letters, a dot, ending in EU. So that one is in the language defined by these rules. So this phrase, not an email address, it's not an email address. It doesn't have the @ sign or any dots. There's another one that fits. This one doesn't end in edu or com, so it's not an email address. This one doesn't fit according to those rules, but maybe we need to fix the description to allow for some numbers, say. And actually specifying precisely what's a legal email address and what is not a legal email address can get pretty complicated. So this is just to indicate that it's not always so easy to specify the rules. So the challenge is we want to develop a precise description of the set of strings in question, and that's true for many of these types of problems. And we'll look at a way to do that soon. Here's a third example from genomics. So nucleic acid is one of the letters A, C, T, or G, and we've seen examples before with this representation. A genome is a string of nucleic acids. So there's a thing called a Fragile X syndrome pattern. And so that's a genome that is defined by the following rules. It's got GCG somewhere inside, followed by any number of CGG or AGG triplets, followed by CTG. And in fact, this is important because the number of triplets correlates with this Fragile X syndrome. So if you have a genome, you might want to know this in order to deal with this illness. So given a genome, does it have the pattern? Well, so what about this one? Does it have this pattern? This example is to illustrate the challenge of the pattern matching problem. And the answer in this case is yes. After a while, you can find a GCG, and then there's 3 CGG and AGG triplets, and then it ends with CTG. So that's 3 examples of a fundamental computational problem with all kinds of applications. So the tool that we use to address these types of problems is called regular expressions. It's a notation for specifying a set of strings, otherwise known as a formal language. So regular expression, an RE, is either the empty set or an empty string, or it's a single character or a wildcard symbol that represents all characters, or it's an RE enclosed in parentheses, or it's the concatenation of 2 or more REs. So here's examples of these rules. So AAB, that's the concatenation of a bunch of single characters. That specifies the set consisting of that one string. So only that string, AAB, is in the set specified by that regular expression, or in the language defined by that regular expression, and every other string is not in that set. If we use a wildcard character, then we can specify multiple strings. So we say .u, 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 that's all the 7-letter words with alternating u's starting at the second character. And there may be lots of words in the dictionary. These are the ones in the dictionary, but of course it specifies any string of 7 letters with those u's in there. So those are examples of strings that are in the set specified by that regular expression. And then if you don't have the u's strictly alternating like that, then it's not matching. So that's simple examples of regular expressions using concatenation and wildcard. And then we can have more complicated operations for the union of 2 or more regular expressions. That's just one or the other, and we represent that with a vertical bar. So in this simple example, only the 2 strings, AA and BAAB, are in the language defined by that regular expression, and every other string is not in the language. And then there's what's called the closure, and that's any number of occurrences of the RE. So A, B star A means A followed by 0 or more occurrences of B followed by A. So AA, A, B, 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 A followed by any number of B's followed by A is in the set defined by that string, that regular expression. But these other strings are not in the set defined by A, B star A. First one doesn't end in an A, the second one's got an A in the middle there that's not allowed by the definition. Just interesting to note that the closure operation already takes us to infinity. That's specifying an infinite set of strings. The number of B's is not specified, could go without bound. And then we can use parenthesization to make up complicated expressions describing specific sets. So for example, A followed by parenthesized A or B, AAB, again there's 2 strings that are in that set, AA, AAB, and AB, AAB, and every other string is not in the set defined by that regular expression. Or if we say A, B star A, that's a way of saying alternating ABs ending in A. And if you have 2 A's in a row or 2 B's in a row anywhere, it's not in the set defined by that regular expression. Again, an infinite number of strings. These are simple rules, easy to understand, but it turns out to be a very expressive notation for specifying sets of strings. So for example, dot star, SPB, dot star. That's all strings that have SPB inside them somewhere. This type of thing is useful for solving a crossword puzzle. You're often interested in answering questions of this sort. And we could also add the condition that it must be in the dictionary and describe our set that way. So the raspberry and crisp bread are in the language defined by that regular expression, but these other ones do not have SPB in that order contiguous anywhere inside. And the dot star just allows matching of any number of characters, so wherever the SPB is, that's would be matched as long as it's somewhere in the string. Here's a much more complicated one. A star, or in parentheses, A star B, A star B, A star B, A star, whole thing starred. With a little thought, you can convince yourself that this specifies all the strings consisting of just A's and B's, where the number of B's is a multiple of 3. So BBB, just take all the stars to mean 0 occurrences. AAA, that's, we can take the star on the right to be 0 occurrences. So it's got 0 B's, we'll count that a multiple of 3. But if you have a multiple of 3 B's anywhere in there, you can match it to that regular expression. It's in the language defined by that regular expression. If you don't have a multiple of 3 B's, then it's not in the set. Already we're starting to see a little bit of computing just with this simple notation. So here's another one just using dot star 0 dot dot dot. That just matches all strings that fifth to last digit is 0. And here's one for our fragile X syndrome pattern. Dot star, and then we put that GCG followed by any number of occurrences of CGG or AGG star, ending with CTG, and then finish with dot star. So if a genome has the fragile X syndrome pattern inside it, that's the way to specify that language, and the ones that don't does not match. Again, very expressive, and actually it's so useful that many extensions have been developed, just additional operations that make regular expressions even more useful, because sets of strings is something that actually we wind up wanting to specify in all sorts of applications. So for example, rather than star, we can use plus, and that just excludes the possibility of 0 occurrences, so 1 or more occurrences. We can specify a class of characters by putting a range. So little a to little z would be lowercase characters. Big A to capital Z is capitalized characters. And inside the brackets, it says take a character from that sequence. And with that, we can check capitalization, or we can specify languages that have proper capitalization. Rather than plus or star, you might want to say exactly a certain number of occurrences. So that's within curly braces. So this says take a 5-digit number followed by a 4-digit number. So maybe that specifies whether the string is a zip plus 4 code. There's all kinds of other strings that are not in the language, but at least you can test whether it's legal according to the rule. Or maybe between J and K occurrences. So that's curly braces 2 comma 4, that says 2, 3, or 4 occurrences of dot, which would mean a wildcard character. So that's A and B separated by 2, 3, or 4 characters. Negation, so that's specify a set of characters and say anything but those set of characters. So this generalized regular expression says 6 characters that are not vowels, and that's a word in the dictionary, 6-character word in the dictionary without a vowel. And then there's special characters like white space. So a typical convention is to have \s match any white space character like space, tab, and newline, and other things like that. And that's useful when processing text. Now, it's important to note that in applications, we're going to want to use these things all the time. From the point of view of the theory, they're just shorthand. They're not essential to understanding the fundamental theoretical points that we're going to talk about. So you can always replace one of these shorthand notations by a regular expression that follows the rules using parentheses or star concatenation only. So here's just an example of the applications that we considered. How do we write a generalized regular expression that specifies these rules? Well, it's pretty straightforward. These rules are quite specific, and with the generalized notations that we've talked about, developing the generalized RE for that is pretty straightforward. So we have a C, and then we have a dot 2 through 4, and we have to have the proviso that in this case only the allowed letters representing amino acids are in the alphabet. So that's 2 to 4 of them, and then a C followed by exactly 3, and then something from the one of the characters LIVMFYWCX, followed by 8 of them, followed by an H, followed by 3, 4, or 5 of them, followed by another H. A pretty compact notation of those rules that is a useful way to specify it. Not hard to learn these rules, and it's something that everyone who's going to use computers effectively learns to some extent eventually. Here's a real-world application having to do with proteins, and actually scientists, biologists use this website as an integral part of their work. And searching in there has to do with typing a regular expression in that window and getting the result. And more other search type tasks are involving regular expressions because it's an easy to use and compact notation for specifying what it is that you want to see. So here's just another example with our email address idea. And so this is again a generalized regular expression. It says at least one lowercase character followed by @, followed by a sequence of at least one string of lowercase characters, followed by a dot, followed by an edu or com. And again, as an exercise, you can figure out how to add other types of extensions or numbers or whatever else. It's, again, a very expressive way of specifying a set of strings that you want to consider to be legal, or a language that you want to know if is a given string in that language. So now what we want to do is, given that setup, now we have a formal and specific way to specify sets of strings or languages. And now we want to know how we can determine whether or not a given string is in the language or matches the given regular expression. That's going to be our next task. Here's just a couple of pop quizzes, and again, worthwhile to study these types of questions to make sure that you understand the basic idea. So in any kind of quiz or exam on this material, you might be asked, which of the following strings match A star, BB, AB, or BA star? Well, you have to figure out a way to get through this question by just working through. In this case, what do you think about ABB? Well, looking at the RE, the star says take any number of A's. I can certainly just take one, and then I take the BB, and then the rest of it I'll take 0 occurrences of. So that one certainly is in the set it describes. What about the second one? Second one doesn't work because every string in that language has to have 2 consecutive B's in it. What about the third one? Again, after this one, after you get the BB, there's no way to get just a single A at the end. You have to have AB or BA. So that one doesn't work. That one does. No A's, 2 B's, then take a BA and an AB. And that works. There's no C anywhere, so number 5 is easy. And this one is more complicated reasoning to figure out why that string is not in there. Don't have an even number of characters after BB. So you can see immediately, not so easy to know whether a given string matches a given regular expression. Okay, here's another one, a type of question that you would have to answer in any kind of quiz on this material. Given RE for genes, and genes are described this way. You have characters are ACT or G. Every gene starts with ATG. The length is a multiple of 3. And it ends with either TAG, TAA, or TTG. So think about how you would create a regular expression for, that implements those rules, describe the set of strings that satisfy those rules. Here's the answer. At the beginning there has to be an ATG. At the end there has to be one of the 3 codons TAG, TAA, or TTG. In the middle you have A or C or T or G 3 times any number of occurrences. We could have used the modified dot notation saying just anything from the alphabet if we had wanted, ... star. So that's a second example, and it's worthwhile to go to the book site and practice on other examples of regular expressions and whether or not strings match them. Next we're going to look at a simple abstract machine called deterministic finite automaton. And remarkably, this simple machine is going to help us with the problem of determining whether or not a given string is in the language described by a given regular expression. So let's describe and define a deterministic finite automaton. It's an abstract machine that actually is built for the purpose of solving a pattern matching problem. That is, there's a string specified on an input tape. No limit on the length of that input tape. The string can be any length, whatever. And what the DFA can do is to read a character on the input tape exactly once, moving from left to right. It gets to read the character and then move on to the next character. After it's read the whole string, it's going to light up the yes light if it recognizes the string, the no light otherwise. So it has internally programmed the idea of what set of strings it's going to recognize, and it reads the whole string and then lights up the light depending on whether or not it recognizes it. So with that, each DFA defines a language. It reads a string, it can read any string at all, and for some of them it lights up the yes light, and those are the ones that are in the language it defines. And for other ones, it lights up the no light. Those are the ones that are not in the language that it defines. So complete correspondence between DFAs and languages or sets of strings. So let's look at how to make a DFA and look in more detail. So here's an example of a DFA where we talk about actually what's inside. So the first thing is it's got a finite number of states. So those are the circles in the diagram inside. And each one of the states is labeled Y for yes or N for no. Also, there are arrows or transitions between the states, and each one of those transitions is labeled with a symbol. The other thing is that one of the states is the start state, and that's the one, in this case, at the left with an arrow from nowhere pointing to it. So the way the rules that govern the operation of the DFA are listed as the bullet points. We begin in the start state, read one of the input, the next input symbol, and move to the state that it indicates from our start state. So every state has a transition leaving it labeled with each character. So whichever character it happens to be, that says which state to go to next. And we just keep going until we've read all the input. And then we're going to be in one of the states after that process. And if we're in a yes, we light the yes light. And if we're in an N, we light the no light. So let's look at an example for how this DFA operates for this string. Is this string in the language defined by this DFA or not? So we're in the start state and we read a B. So it says that what we should do is read that B and go to the middle state. Now we're in that state and we read a B, and again we go to the right. Now in that state we see an A. In the state at the right we see an A, and the transition says just read that A and stay in that state. And again, read that A and stay in that state. Now we have a B, so we go back over to the first state on the left, read a B, go to the middle state, read an A, stay there, read a B, go to the state on the right, and read a B, go back to the start state. Now we've read all the characters, and we're in a state labeled Y, so we light the yes light. So we say that that DFA recognizes that string, or the string is in the language defined by the DFA, the set of strings defined by the DFA. Here's another example. Another string, same DFA. Read the B, go to the right, read an A, stay there, read another A, stay there, read a B, go back to the left, read a B, go to the middle, read an A, stay there, read a B. Now we've read all the characters and we're in a state labeled N, so we light the no light. That string is not in the language defined by this DFA. Very simple set of rules. And every DFA, as long as it has states, with transition for every character that it might read for every state, can follow these rules and eventually either light up yes or no. DFA operates according to very simple rules. One thing that we can do to better understand it is to write a Java program that simulates the operation of any DFA. This is what we do to get our examples and quiz questions and so forth. So what's that going to look like? The instance variables, well, there has to be the start state. And then we have a Boolean array that says whether it's a yes or a no, or does it recognize the string or not. And then we have an array of symbol tables. For each state, we have to know for each character what state we go to next. For example, for state 1, the one in the middle, we want to, if we get an A, we want to go to state 1. If we get a B, we want to go to state 2. So we have a little symbol table mapping A to 1 and B to 2. Those are the those tables represent the data structures that we need in order to represent a state in the DFA. And then, so our constructor takes a file, and we have a file format that basically has the same information, and the constructor will just read that in. Maybe this is our file format, which is the number of states, the alphabet, the letters that we have to worry about seeing on the input, the start state, and then the values needed for these tables. And so any of us can write a program to read that file and to fill in those data structures. So what's interesting is the routine recognizes, which takes the string on standard input and simulates the operation of the DFA, returning true if it recognizes the string and false if it doesn't. So we start at the start state, and then, we take the string as a parameter to this, as an argument to this method, and then we want to print out whether or not it's in the language recognized by the DFA. So for every character in the string, all we do is get that character, so it's input.char@i, and then we get the state that in the symbol table. So next of state is the symbol table, .get gets the entry corresponding to that character, and that's a state, and we just reset the state to that. And then when we're done, we've read all the characters, then we just return true or false depending on which state we're in. And so our test client can make a new DFA from a file name given as argument. And then it can read through standard input and can read a string and then print out yes if the DFA recognizes it and no if it doesn't. For example, we can run it and say, well, is BA in there? And it says yes. What about BB? It says no. And we can type in any string we want and have a simulation of the result of running that DFA to recognize that string. Pretty interesting idea that we can, with really a one-liner, simulate the operation of this abstract machine. It's an abstraction, but we can write a program to try to understand what it does. And that turns out to be a key concept in theoretical computer science that we'll come back to again and again. So here's just, again, like the pop quizzes on regular expressions, you have the same kind of thing on DFAs. And these get to be pretty complicated. We actually really need these programs to check these kinds of questions. They make good quiz questions, and you'll certainly encounter them if you have any kind of quiz in this kind of material. So which of the following strings does this DFA accept? Does it accept the set of bit strings that end in 1? No, because it accepts 0, 1, 1, 0, say. And that one doesn't end in 1. And there's lots of strings that, that it doesn't, that don't end in 1 that accepts, but to answer the question, we just have to find 1. It's kind of easier to say no than yes for this kind of question. Equal number of occurrences of 0, 1, and 1, 0. Well, no, there's plenty of examples. Bit strings with more 1s than 0s? No, you could do lots of 0s in the first state and then a 1 with lots more 0s than 1s. Equal number of occurrences of 0 and 1? No, these strings that we just gave, this one that we just gave disproves that. Bit strings with at least 1, 1. Yep, that's the one. And there you have to reason that it accepts all those bit strings and only those bit strings. That's why these types of questions are challenging to answer often. Here's another example. So what following sets of strings does this one accept? Well, does it accept the set of bit strings with at least 1, 1? Well, no. In this case, here's a bit string that's got 1, 1, but it doesn't accept it. Its first transition stays in the no state, then the 1 takes it over to the yes, but then 2 zeros, it winds up in the no state. So it's in that language, but this one doesn't accept it. Equal number of occurrences of 0, 1, and 1, 0. Again, same argument. This string will wind up in the no state, so it's in the set, but it doesn't accept it. More 1s than 0s? Well, no, that's not it either, and you can reason yourself why that one's not it. Equal number of occurrences of 0 and 1? No, that's usually a tough one when you've got a loop, because you can just spin in the loop as long as you want. Actually, this one's a kind of complicated way to recognize a pretty simple language, just the bit strings that end in 1. The only thing you can say about a bit string in this language is that in the language recognized by this DFA is that it ends in 1. Again, studying these types of questions and looking for others in the book or in the book site is a worthwhile activity to better understand DFAs. Now, why do we talk about DFAs in the context of regular expressions? Well, there's a very important reason, a theorem going back 50 years or more now, more than 50 years, called Kleene's theorem. And it's an observation based on the idea that we've just seen two different ways to define languages. We've seen regular expressions. You give a regular expression, it defines a set of strings. And we've seen DFAs that also define a set of strings. So for example, the set of all strings made up of the characters A and B with the number of occurrences of B is a multiple of 3. That's the DFA, the one that we've looked at, and that's the regular expression. Two different ways to define sets of strings. Remarkable fact is that these two ways of specifying sets of strings are equivalent. So that is, given any regular expression, there's a DFA that accepts the same set of strings. And given any DFA, there's an regular expression that matches that same set of strings. So they're equivalently powerful. Now there's sets of strings that you can't specify with either one, and we'll talk about that later on. But the idea that these two models of specifying languages are equivalent is really a profound idea. And for now, the consequence of this is there's a way to solve the regular expression pattern matching problem. What we can do is, and Kleene's theorem gave a constructive way to build the deterministic finite automaton corresponding to the given RE. That's how we proved there exists an automaton, is he gave a way to build it. And then use our program to simulate the operation of the DFA. So that's a fine way to solve the RE pattern matching problem from Kleene's theorem, and that's what we're going to examine next. Next, we're going to talk about applications of this theory, and then we'll go back to the fundamental theoretical questions. So the most important application is a solution to the pattern matching problem. It's called grep. And it's based on the idea of Kleene's theorem, which given a regular expression, we build the corresponding, a corresponding discrete deterministic finite automaton, and then simulate the operation of that machine. Now in practice, there's a difficulty in this, in that the DFA might have exponentially many states for some kinds of REs. So that limits the use of this specific algorithm in practice. But very soon after, a much more efficient algorithm that uses what's called a non-deterministic finite automaton, an NFA, was developed. And that's the one that's the basis of grep. And the NFA we'll talk briefly about later on. It's kind of an imaginary device where the finite automata can go of one of two different states for any given character, and it figures out the right one to go to. It's kind of a mind-blowing concept, and you can learn more about that in an algorithms course. We will talk about non-determinism again later. So that method is called grep, Generalized Regular Expression Pattern Matcher. It was developed by Ken Thompson, who won the Turing Award in 1983 in part for this work. And grep is everywhere. It's been an indispensable tool for programmers and anyone using computer effectively for decades, and now you find it built into systems of all kinds. It's in many development environments, including Java. And we'll look briefly at how it's found within Java next. You can get a t-shirt that says grep will find you. And there's many, many other products you can find out there. So the first thing is that Java's string class actually implements grep. So there's a method called matches that takes as argument a string, and that string can be a regular expression that's built according to the rules that we've described. And then it returns true if this string matches that regular expression and false otherwise. So if we put in a string RE, and this is our description of the finger domain protein thing, and then we have a specific string, then we can say zinc finger dot matches that regular expression, and in this case we'll get true. So right away the capability of recognizing regular expressions is built right into Java, and it's definitely worthwhile to use it in these sorts of applications. So here's just an example of a client. You can write a program that takes a regular expression from the command line and that takes strings from standard input and then validates whether or not those strings are in the set defined by the regular expression. So we take our regular expression from the command line. While standard in is not empty, we'll read an input string, and then we'll just print out the result of input.matches, the regular expression given on the command line. All kinds of applications for this that we've discussed in our examples of regular expressions. You might want to type the zinc finger domain thing, and there's a few things that you have to worry about in terms of quotes around the string, but they're details. And then type in a string and it says, yep, that one's in there, or type in another one, it says, no, it's not. So if you know the regular expression, then you might not have to go to the website. You can deal with problems like this on your own. This is another example that is maybe useful in programming languages. This is an example of what's a legal Java identifier. So ident123 is legal, but 123 ident is not. You can't start with a number. It's just another example. And here's our email example, our simplified email address example. And again, this stuff is all built into Java, so for a broad variety of applications, you can put a regular expression on the command line and then a bunch of strings and try to understand how that regular expression is working, validate whether or not the strings that you have are in the language described by the regular expression. That's a very simple client. There's actually many other useful methods related to regular expressions built into Java. So you can use search and replace defined by regular expressions. And then what's called parsing is taking a string and dividing it up according to the appearance of substrings matching a regular expression. And I'm not going to spend a lot of time with this. Not appropriate to cover this level of detail in lecture, but wanted to make people aware that there's quite a bit of powerful string processing built right into Java's string class. So for example, you can call replace all for a given string, and its first argument is a regular expression. And the second argument is a string, and you can just replace all occurrences of the substrings matching the regular expression with your given string. And this is useful to clean up data of all kinds. We'll see some examples. Or the other thing is to split the string around occurrences of or matches of the given regular expression. And then that, if there's a lot of occurrences of the regular expression in our big string, then this will make an array of the substrings that appear in between. And again, we use this in all kinds of applications. So here's an example of cleaning up data. Where we want to clean up white space in a text string. So we want to process a text string, but we don't care if there's 3 spaces between words or 1, or if there's a tab or a new line. We want all of those to be treated the same. So we have this tricky notation that often comes up in string processing, where we have to use a backslash or 2 backslashes to specify a single one. So what this means is 1 or more whitespace characters. And so then if we have a string that we read everything on standard input, say the contents of a web page, then we can call replace all to replace all contiguous occurrences of whitespace with a single space. So that's really useful. That's where we get our examples of text for various algorithms. Or we can use split around the white space and just get the distinct words in a big input text. A little bit for experts, but not so much. Once you've seen a few examples like that, you can see ways to take big strings and clean them up and process them, and we do this quite often in our examples for this course. You can even go way beyond. This is an interface defined for professionals, but it's still worth a study, where actually what you can do is there's special classes for taking a regular expression and creating really the machine, the pattern matching machine that can find substrings matching the pattern in the given input stream. And this gives even more flexibility in processing strings. And again, I'm not going to take the time to go through the details of these implementations, but if you're interested, they're worth studying, and they're quite related to the basic concepts that we've been talking about. So here's an example of a client that uses this stuff. And I won't, again, go through the details of the client, just to show the types of things that are possible with just a little bit more study. So maybe you want to harvest information from a huge input stream. So what we do is take the regular expression from the command line, take our input from standard input, a file or a web page, and then print all the substrings matching the regular expression. And this is not built into the string class. We have to call these special classes built for regular expressions. You can see there in Java util regex. So here's what the code looks like. So first thing is to just take our regular expression from the command line, then build an input stream, and then read the whole thing, and that's our input string. Then we build a pattern which takes the regular expression and compiles it into basically an automaton that's going to go through the string. Then we build a matcher out of that. And as long as matcher finds the occurrence, we print out what we've seen since the last occurrence. That's what the group is. Pretty simple code, and again, not my intent that everybody should understand every line of that code, but if you study it, you find it to be useful. So if we have a chromosome and we go ahead and look for our Fragile X syndrome, we can print out all the occurrences of it in that one chromosome. And that can be hugely, a huge file, a thing like that. And then again, it matters how many occurrences of the triplet appear, but the CGG and the AGG appear between the two endpoints. Or you might want to get email addresses. So this is a command that we've shown in class for many years for harvesting email addresses off a web page. And you might expect to get our emails out of there. Actually, that doesn't work anymore, probably because we've been showing this slide in class, because there's no email addresses on that site anymore. And that's true of many sites. Just for this reason, it's so easy now to harvest emails in this way. In summary, regular expressions and DFAs, which we use to recognize languages defined by regular expressions, are useful in all kinds of applications. These are just a few that we're listing. You certainly will encounter them as you use computers for more and more sophisticated applications. So our point of this last section is to convince you that theory is useful, but next we have to really get into the basic theoretical questions surrounding this. So sure, grep and facilities like that are built into many, many systems that you'll be using, but it's only the tip of the iceberg as far as the theory goes, and that's what we'll look at next. The concept I want to begin with in introducing theoretical computer science is the idea of limitations on the power of computing. So let's see where we are. So for programmers, regular expressions are really a powerful pattern matching tool. We have a paradigm based on the theory that really facilitates the implementation, and the combination of the two are very important in the real world. For theoreticians, there's the idea that we have two different ways to describe sets of strings, and we know they're equivalent, but it's interesting to think about, are there sets of strings, are there languages and machines that can describe sets of strings that we can't do with REs and DFAs? I alluded to the fact that there are, but what are they? How do we address the idea of characterizing those types of languages and machines? Certainly the DFA is an extremely simple machine, and we imagine there must be machines that are more powerful in the terms of having the ability to describe a broader class of sets of strings, but what are those machines like? For you, as we mentioned, you've got the core principles of computer science introduced, the basic idea of abstract machines and languages. And we're going to use those things to get started on really addressing fundamental questions in theoretical computer science. So here's the basic idea. So are there sets of strings that can't be described by any regular expression? And the answer is yes, there are. And we're going to do an actual mathematical proof that shows that you can't have an RE that describes the bit strings with equal numbers of zeros and ones. And that's just one example. There's many other examples. Strings that represent legal regular expressions. There's no regular expression for describing those. Or prime numbers, or another example from biology, a complemented palindrome or palindromes. There's a long list of sets of strings that we'd like to work with that regular expressions are not powerful enough to describe. And you might say the same thing about DFAs. Are there sets of strings that can't be described by any DFAs? And of course, by Kleene's theorem, that's the same question. You can't build a deterministic finite automaton to recognize, say, bit strings with equal numbers of zeros and ones. And if you prove that, then you've proved that you can't have a regular expression that specifies that language. So that's a basic question, and let's first be sure that we have a good answer to that first question. Why is it that we say that deterministic finite automata are not sufficiently powerful to do what we want? We have a limit on the power of these abstractions. So our proposition is there exists a set of strings that can't be described by any RE or DFA. And we're going to actually do a proof. We try not to do too many proofs in this course, but a couple of them are really important. And this one you'll be able to understand. So what we're going to do is prove this by showing that for this specific language, the set of bit strings with equal number of zeros and ones, no DFA can recognize that set. So our proof is going to be by contradiction. So let's assume that we do have such a DFA. It's a finite automaton, so that means the number of states is finite, so we can just say there's a number n, which is the number of states. So that's our first thing. Let's assume that we can do that. So, it's supposed to recognize strings with equal number of zeros and ones, so it's going to recognize the string that has n plus 1 zeros followed by n plus 1 ones. So for 10, so we give it 11 zeros and 11 ones, and it's going to go ahead and recognize that. So we don't know what sequence of states that it goes through, but it's going to go through some sequence of its states. It doesn't matter what it is. As it reads each zero, it's going to, whatever complex construction it is, it's going to go to some state. And each time it's completely defined what state it goes to next. Whatever state it's in, follow the zero transition out. Now the critical thing is that since there's only n states, and we have n plus 1 zeros, some state's going to get revisited. There's not enough different possibilities to get through that without having some state getting revisited. But that's crucial because what happens next only depends on being in that state. So what that means is if you take the zeros between the visits of that state, the machine can't tell the difference. It's going to, whatever it does on that string with equal numbers of zeros and ones, it's going to do on this other string. It's going to start out 0, 3, 5, and once we're in position 5, it's going to do precisely the same thing for those two strings. So there's a string with equal numbers of zeros and ones that it may recognize, but there's another one that has fewer zeros than ones that it's going to recognize too. That string does not have equal number of zeros and ones, and that's a proof by contradiction. It's recognizing a string that we said it didn't recognize, so the assumption that we started with, that such a DFA exists, must be false. That's a proof that there's a set of strings, and a pretty simple one, that can't be described by any DFA or regular expression. So that's a first result in theoretical computer science. There's a limit on what we can do with this kind of machine. So it's a natural question to ask is, so is there a more powerful machine? Like, for example, is there one that can recognize this language, equal numbers of zeros and ones? And the answer is yes. What we can do is add a stack to the deterministic finite automaton. I won't give the details, but I'll give a demo and you can understand how this machine works. So with this machine, you get to, if you want, in a state, put the character that you just read on a stack. So let's look at how that one works in this example. So we read a 0, we put it on the stack. Read another 0, put it on the stack. When we read a 1 and we have 0 on the stack, we pop. But if the stack's empty, we put the 1s on. And now you can see that whichever character has appeared more is going to be on the stack, and it essentially counts the imbalance between the zeros and the ones. And if the stack is empty and we get to the end, then it lights the yes. So that's a more powerful machine that can recognize this other language. It's interesting that just by adding a stack to a DFA, we can make it recognize more larger language. There's also a formal language, more complicated than regular expressions, that defines the same set of strings. There's a duality between machines and languages, but we're going to focus on machines just for now. So what about more powerful than a one-stack DFA? Yeah, actually, there's languages out there that if we add a second stack, we can recognize prime numbers, we can recognize strings that are legal Java programs, many other things. And again, won't do the details of that just now. That's really about the next lecture. This is the way a theoretician thinks. I've got the simplest machine I could possibly imagine. And if I add a stack, I can do more than with the simplest one. If I add a second stack, I can do even more. And the question is, where does it stop? So we'll talk about this one next lecture. But the thing is there a machine that's got more power than a two-stack DFA? Can we add a third stack and then recognize even more languages? And the amazing answer is that no. Not even a room full of supercomputers is more powerful in this sense than a two-stack DFA. That simple abstract machine, from this standpoint, is equivalent to a room full of supercomputers. It's a basic limitation on computation that we're going to talk about in the next lecture.